Yes, good afternoon, ladies and gentlemen. I'm Wimol. I'm from Thailand. It was a long journey from Thailand to here. I took about more than 20 hours from my country to be here. Yes, very nice to see everybody here. It is my pleasure to give a presentation on a cost-effective true random bit generator using a pair of robust signal-based chaotic maps. Well, the first question I would like to ask everybody here is, what is a true random bit generator? The true random bit generator, or TRB, is typically defined as an algorithm or some devices that enables the generation of random digital sequences. Of course, they are commercially available like IBM's or Quantis or Sun Crypto Accelerator 1000 like this. But these are very expensive because they use the quantum techniques to generate the random number, or we call these techniques are stochastic system. And why we need a true random bit generator? Of course, we use for the security issues for cryptography applications like the leader here. We encrypt, we get this scrambling picture on the text, we get a ciphertext like this. So the true random bit generator is very important for these kind of applications. Of course, how to generate true random bit generation in the existing techniques. The first technique is the quantum noise amplifications, of course. For example, the electrons, when you, like in the resistor, when you supply the voltage, the electrons might vibrate and it generates noise. So we use that noise and then you amplify it and threshold it. You're going to get some kind of random bits as well. And the second one is the digital techniques, of course. Well, it seems to be easier and cheaper than the first techniques, but it's very complicated. You need at least like 8 flip-flops to generate. Well, there's a limitation. For the quantum noise amplification, the system is very expensive, requiring many devices. But for digital techniques, are you sure? It's not guaranteed, okay? And large number of flip-flops are required. That's why I propose the chaos-based true random bit generator. But before that, I would like to tell you why chaos theory can be used for the true random bit generator. Let me tell you about the chaotic system. Of course, when we talk about the linear system like this, everybody could guess the answer very easily because you can get the equation very easily, right? But for nonlinear system like this, like a clouds or like this one, it is very difficult to find the equation. So, chaos theory gives you a deterministic system. It's a dynamic system that can be represented by equation. And there are 3 natural features of chaos. The first one is a deterministic nonlinear dynamic system. That means in your equation you must have at least one nonlinear terms, and it is very sensitive to the initial condition, okay? And the third one is the random output values, unpredictable. There are 2 kinds of system I would like to give you here. One is the chaotic maps, or one-dimensional system. For example, the well-known logistic map like this. It can be written in this equation. You could see that the output in time domain is random. And if you focus on the bifurcation like this, okay, you could see there are some regions, the thick regions represent the chaotic regions, but there are some kind of, white region here. It is not chaos, okay? And the next system is the chaotic flows, or the 3-dimensional system. For example, a well-known Lorentz system, or I don't think somebody ever heard about the butterfly effects, right? So it is represented by the ordinary differential equations for the 3 system like this, and you could see that the trajectory or the space of this system looks like a butterfly, okay? And the output is random as well. Well, for this system, when you put this kind of ordinary differential equation into some programs like MATLAB or Python, it really takes time because we need specific algorithms to calculate for this kind of ordinary system. So this we're going to focus on the logistic maps. Well, I would proposed a robust signal-based chaotic maps. Okay, actually, you could see that this one is a well-known chaotic maps, well-known cubic map. The cubic map means xn to the power of 3. So the nonlinear is like this, of xn power of 3. And there are some variants. Okay, this one I propose to use the hyperbolic tangent, be beta xn. So we change the nonlinearity in this shape, but it still gives very chaotic features as well. But in particular, in these papers, we present an alternative of the nonlinear terms, x to the power 3 or the hyperbolic tangent by using the hard switching signum function. This is the signum function. I think everybody knows that the signum function gives the value of -1 when it's lower than 0. If it's greater than 0, it's going to be 1. We use the hard switching signum function. Let's see the result. This paper further generalized to signal-based chaotic maps. Okay, this is the equation that I propose to you. It includes one linear terms and the signum terms. This is non-linear terms. And for the Jacobian analysis, this one is in order to make sure that your system is not stable. If it's stable, it won't give you the chaotic signal rate. So we need it not to be stable. So the Jacobian analysis, this is the typical way. If the Jacobian is greater than 1, that means the system is unstable. And it is preferable in this case. And the equilibrium. For case 1, we get 3 equilibrium points. And case 2, we get 3 equilibrium points. You could notice one thing. The sign of this term gives different characteristics of the systems. Let's have a look here. I say my system is robust. Why? You can see from the bifurcation here. The bifurcation, there's no kind of, the thick area is really thick. There's no separations. Okay? So this is robust chaos. We can use any value from like 1.4 to 2 like this. Okay? Even the value change is still be chaos for the two cases. You could see that this one is the Lyapunov exponent. When it's greater than 0, the Lyapunov system is the parameter that indicates whether the system is stable or not. If it's not stable, it becomes positive. You could see that from this region, from 1 to 2, the value of Lyapunov exponent is greater than 0. This one as well. The two systems give the same characteristic of bifurcation and the Lyapunov exponents. But for the cobweb plots, as I mentioned before, there are 2 or 3 fixed points. This one chose for the first system, the cobweb plot is like this. But for the system number 2, the cobweb plot is like this. This one is the 2 fixed points. And when you consider in the iterations from the current stage and the next stage, it's going to go outwards from the fixed point. So each particular system has particular pattern of the cobweb plots. And finally, you could see that this is the output signal in time domains for the two systems. They are randoms. Here, we use a very simple technique to get the random bits. We just thresholding using a very simple programs like this. And then we put the input by the post-processing system here, the chip register, in order to synchronize the clock. And for the test condition, of course, there might be a question, are you sure that your system is random, the output is random or not? Of course, we test by NIST, the National Institute of Standards and Technology of the United States. They provide a statistical test suits in order to evaluate the randomness of binary sequences. So I generated about 1 million bits and put into these programs. There are 15 test methods and the p-values, okay? A p-value greater than a typical confidence level of 0.01, that the sequence is considered to be random with a confidence level of 99. You could see that for the 15 tests, it passed all this kind of 15 tests. And this is the hardware verification. We use a very cost-effective Arduino. I think everybody knows that. This is the chaotic signal from system 1 chaotic signal from system 2, and after thresholding we got some kind of looks like digital like this, and you could notice from this spectrum, because the signal doesn't have any single frequency. There are many frequencies inside there, right? So the spectrum is relatively flat. And we put into cost-effective Arduino, and finally we got a true random bits like this. I'm gonna go for the conclusion. The proposed new chaotic maps that generates random signal. I employ chaotic signal to generate random bits. The random bit has all the NIST tests, and the implementation on microcontroller has been verified. Thank you very much. Any questions, please?
These questions.
Yes,
how
sir.
about the cost effective?
Sorry?
Cost effective?
The cost effective. I could say that, you
You
know.
not mention anything about it.
Okay.
Right.
For the commercialized random generator is about like maybe 500 pounds. In my case, I use single microcontroller. It's about 2 pounds.
Okay.
Very cheap.
Thank you.
So I put all algorithms into the controller.
Okay.
Yes. Because I think the reason is because they use the quantum techniques. So sometimes they need a very expensive devices.
Okay.
Yes.
Thank
Thank you.
Please. Any companies which you want to implement it to sell it?
Well, actually, I am contacting to the military division in Thailand to use this kind of, you know,
So there are potential
cryptography.
customers, yes.
Yes.
Yes. Great.
Actually, it's not really, you know, commercialized, but I gotta give it for the government, for the security issues.
So I'm thinking of implementing somebody, yes.
Thank you very much.